Hello everyone, welcome to Calculus Lesson 7.6, Applications of the Dot and Cross Products. We've already looked at one application of the dot product, and that was work done by a force when an object undergoes a certain displacement. So we're going to revisit that idea again, and we'll also introduce the idea of an application for the cross product. So recall, let's say I have a box, and there is a person who is pushing this box across the floor. And so they apply a force onto this box. So this is F applied. I put the arrow on top because force is a vector. And after some time, the box ends up at a further distance. So let's say this box travels a distance delta D. Okay? And because it's in a certain direction, we can actually call that a displacement. Now, what I want you to notice is that forces act along straight lines. Now, those of you that have studied physics, you would know that this isn't always the case. Sometimes forces do not act along straight lines, although for our purposes, the forces act along straight lines. Now, let's say I don't just have this simple applied force that I'm considering. Maybe I have a box that is hanging by a thread. Now, onto this box, there are two main forces that are acting on it. Now, sure, I can look at this and say there's friction going left, there's weight going down, and there's something called a normal force going up. We're not going to concern ourselves with that. But if we really look at this picture more detailed, we can say that there is a gravitational force going down, and there is a tension force going up. And that tension force is due to the string that's holding it up. So I can look at the work done on the box due to its weight, due to the tension force, on this box due to the applied force, or I can find the total work done on it due to the total force. There's a lot of different ways that I can inspect this problem. Okay, but anyways, we saw that work was equal to the magnitude of force times displacement times cosine of theta. Okay, so that's the angle between the vectors of displacement and force when they're placed tail to tail. So if I'm looking for the work done by the force of gravity goes in the formula. If I want to find the work done by tension, tension goes in the formula. If I want to find the total work, then the total force or the net force goes right here. Okay, so that's what we've done up till now. That's the application of the dot product. Now we have to think about cross product. Okay, so imagine the following scenario. Okay, so you've got a tire. Now, on the tire, you have bolts. If you ever get stuck on the side of the road because you have a flat tire and you have to change your tire on the side of the highway, first things first, be very careful. But second, when you reach in your trunk and you go for the torque wrench, let's say you have two torque wrenches that you find. Okay, so let's say one torque wrench looks like this and the other torque wrench looks like this. Okay, so we've got torque wrench 1 and we have torque wrench 2. Okay, so the question here is, which torque wrench will loosen the bolt more easily? Or said another way, if you have torque wrench 1 and 2 in your trunk, which one are you going to use to loosen up this screw? And I really hope that you say torque wrench 1. Okay, so torque wrench 1 is definitely better in this case because it is longer. Okay, so if you can just visualize that scenario, if you have a longer torque wrench, you don't have to apply as much force. If you have a shorter torque wrench, you have to apply much more force. So this introduces us to the concept of torque. Okay, so torque is a vector. It's represented by this funky looking letter here. This is the Greek letter tau. Okay, so tau is equal to the cross product of R with F. So R cross F. Okay, so again, tau, this is the torque. R, you might think of R like radius, and it kind of is. This is the distance from the center of rotation. Excuse me. So in the case of the torque wrench on the bolt, on the tire, on the rim, you've got this length here. That would be R for 1, and R for 2 is that much smaller. Okay, so if you imagine this thing rotating, it's going to rotate about this center of rotation, which is the bolt, and so that full length is R. F, as you might imagine, this is the force. Now, force is measured in newtons, so I represent my units using square brackets. R is the distance that's measured in meters, and so therefore torque, which is given by R cross F, it's going to be given by the units Newton meters. Okay, so that is the formula for torque. If you just want to find the magnitude of the torque, so the magnitude of tau is equal to the magnitude of R times the magnitude of F times sine of the angle between them when they're placed tail to tail. And what we saw in the last lesson, 7.5, is that if you want to find the direction of the torque, you have to use right-hand rule. So if I have R cross F, I would take my right hand, point my fingers in the direction of R first, and then curl it toward the direction of F. Whatever direction my right thumb results, well, whatever direction it's pointing, in the end, that's the direction of my torque. We will do an example using the right-hand rule in the first example, which is coming up now. Okay, example number 1. You have a bolt, and you have just a regular wrench. So just give me a moment while I draw this. Okay, we've got something like this. Okay, so there's your wrench, and there is your hexagonal bolt. Now, for this particular scenario, we have R. Keep in mind, I mean, you've got this wrench. You're holding this wrench, and you're either going to tighten this or you're going to loosen it. You notice that I went clockwise to tighten, and I'm going counterclockwise to loosen. All right. So this bolt is the center of rotation. Everything, this wrench gets rotated about that point right there in the center of the hexagonal bolt. So I'm going to just put a dot right there. That's where the center of rotation is. R, which is the distance from the center of rotation, well, R is a vector. So yes, it's a distance, but it's also a vector. Now that vector starts from the center of rotation, and it goes to the point where the force is applied. So it's not necessarily the length of the object, but it goes to wherever the force is applied. So let's say the force gets applied in that little hole there. Okay, so we call that value here R. So R is, let's say, 20 centimeters. Okay, and now we're also going to apply a force here. Now the force gets applied on some kind of an angle, and the force, let's say, gets applied like this. Okay, so this is F, and the magnitude of the force is 60 newtons. Now I know that the angle here is 80 degrees. Now, sometimes you got to be careful. I mean, you should always be careful, but just pay attention to where the angle is and what angle that you actually need. Okay, so here's our scenario, and the question here is, what torque is the wrench applying to the bolt? Okay, so there's our question. All right, so we're looking for the torque. So magnitude of torque, it's given by this formula right here. It's given by the magnitude of R times magnitude of F times sine of theta. Theta is the angle between them when they're placed tail to tail. Now, right now, the angle that's quoted to you in the question is the angle when they're placed tip to tip. So what you've got to imagine, well, here's the tail of R. The tail of F is right here. If you take this vector and you just slide it over here, okay, so let me actually just sketch that in. This angle and this angle are going to be the same. So this is still 80 degrees. Okay, so tip to tip and tail to tail, it's going to be the same angle. So 80 degrees is, in fact, the angle we're going to use. That's not always going to be the case, so always be a little careful. So we have 0.2 meters. My force is 60 newtons, and my angle is 80 degrees. All right, so grabbing my calculator, Here we go. 0.2 times 60 times sine of 80 degrees. 11.8 approximately. So 11.8, the units are Newton meters. That is the magnitude of the torque. Now we have to find the direction. Okay, so take your right hand. So this is what we learned in 7.5. Take your right hand, your right fingers, start them pointing in the direction of the first vector, which is R, and then curl them toward F. Whatever direction your right thumb points is the direction of the torque. So R is pointing to the right. So I can put my fingers like this. Now, my force is going in this direction, right? So I can't naturally curl my fingers backward. That means the orientation of my hand is not correct. So I will rotate it so my right fingers still point to the right, but this way my hand is oriented opposite to what it was before. Now I can curl my fingers in the direction of the force. And in doing so, my thumb is going into the page. Okay. So by RHR, remember this is the abbreviation for right hand rule, tau goes into the page, or in this case, the torque goes into the bolt. I hope that makes sense. So the force is causing this wrench to rotate clockwise. Remember, I just said if you rotate it clockwise, you are making it tighter. Okay, you are making the bolt go into the page. It's going into a piece of wood, let's say. Okay, so it's getting tighter. If you are loosening the wrench, so if the torque is going in the opposite direction, okay, if the torque is coming out of the page, that means you're taking the wrench and you're moving it counterclockwise. Okay, so this is always the case. All right. Let's revisit something that we haven't talked about for a few lessons, and that is projection. Okay. Example 2. Determine the projection and its magnitude of v, and vector v is 4, 2, 7, on vector u, which is 6, 3, 8. Okay, so here we go. Projection. Let's remind ourselves what the formula is for projection. The projection of vector v on vector u. Now there were a few formulas we learned here. You want the one that represents the vector that has both the components u and v. So it looks something like this. Okay, so vector u gets used the most. So I'm going to have a vector u on top here. I'm going to have the dot product of u on the bottom, and I'm going to have it multiplied by vector u here. The vector that is the bigger one of vector v on u, so v, it only has one spot here in the numerator. So v dot u over u dot u times u. Okay, so I just have to plug in my values here. So what do we have? Let's take a look. So I've got vector v dotted with vector u all over u dot u, and this is times u. Okay, so v is 427, u is 638, and I also put 638 here, and 638 here, and 638 here. All right. So dot product, you know how to handle that. It's going to be the sum of the products of each dimension. So it's going to be 4 times 6 plus 2 times 3 plus 7 times 8. That's in the numerator of the fraction. In the denominator, I'm going to have 6 times 6, or 6 squared, plus 3 times 3, which is 3 squared, plus 8 times 8, which is 8 squared. Okay, and this is getting multiplied by 638. Notice this is going to turn out to be a scalar. That's why I've kept it in round brackets. The piece on the right, that's a vector. A scalar times a vector is just a scalar multiple of a vector. So it's going to be a vector overall. Okay, here we go. So in the numerator, 6 times 4 is 24. 2 times 3 is 6. 7 times 8 is 56. And the denominator, I have 36 plus 9 plus 64. And again, this is multiplied by 6, 3, 8. Okay. So 24 plus 6, that's 30, plus 56, that's 86. 36 plus 9, that's 45. Plus 64, let's see, what do we get? 109. Okay. Now, you could take that scalar multiple and multiply it to every piece inside the vector. I'm not going to do that, and the reason for that is it's going to make the next part more difficult if you do that. So I'm just going to leave that as such. Okay, so that's the projection. The other part of the question was to calculate the magnitude, right? So calculate the projection and its magnitude. So I have to find the magnitude of this. So if you had already distributed the 86 over 109 to each part, you would be calculating a lot larger numbers. So here we go. The projection of vector v on vector u is, well, we're looking for the magnitude rather. So that's the magnitude of 86 over 109 times 638. Oops. Now the magnitude of 86 over 109 is 86 over 109. So I can take that right out of the absolute value bracket. So it's 86 over 109 times the magnitude of vector 638. Now you know how to take the magnitude of a vector, right? Take the square root of the sum of the squares of the dimensions. So 86 over 109 times square root of 6 squared plus 3 squared plus 8 squared. Okay, so that's 86 over 109, 6 squared plus 3 squared plus 8 squared. Well, we just did that in the denominator here, and it turned out to be 109. So that's going to be times root 109. Now, if we grab our calculator, let's see what this is all equal to. 86 times root 109 divided by 109. And we get approximately 8.2. So the magnitude of that projection is 8.2, and the actual projection is right there. Okay, hopefully that's okay. Let's move on to a dot product example and a little bit of an extension on what we have learned. Okay. Example 3. Okay, so let's say we have a force that acts on an object, and that force is given by the vector 300, 700, 500. So all this stands to mean is that there is a certain amount of force acting on the object, and that you can break it down into an x component of 300 newtons, a y component of 700 newtons, and a z component of 500 newtons. Excuse me. This force acts on an object that undergoes a displacement, let's just call it d with an arrow on top, and that displacement is 3, 1, 12. Okay. So part A, what is the work done in the direction of travel? All right. Now, the work done in the direction of travel, well, it's moving in a certain direction. These are the forces acting on it. It has a certain component in the x. There's the x, the y with y, z with z. So what we're going to do here is just interpret this as the generalized dot product. So for part A, we're going to have work is equal to F times, or F dot D rather. So 300, 700, 500 dotted with 3, 1, 12. And we know how to take the dot product, take the sum of the products of each dimension. So that's 300 times 3 plus 700 times 1 plus 500 times 12. Okay, so we just have to punch those numbers. Okay, so 300 times 3, that's 900, 900 plus 700, that's 1600. So 1600 plus 12 times 500, that's 7600. So let's remind ourselves what the units are. Those are joules. Work is a form of energy. And no matter what type of science you studied, you would have seen that energy is measured in joules. This is the accepted unit. Sometimes you might express it in different units depending on your application, but usually it's joules. Okay. Now part B. What is the work done against gravity in order to find the work done against gravity, you have to find the work done by gravity. Now, gravity acts straight down. So gravity acts straight down. So just ask yourself, well, what direction is that? What is straight down based on my Cartesian coordinate system in 3 dimensions? Well, that is the Z direction, okay? In fact, technically, gravity is going in the negative Z direction, but the Z direction is what we really care about. Okay, so if this object is applying a force of 500 newtons in the Z direction, that means that's the component of the force that's acting against gravity. Okay, and so what we only care about, since we only care about the Z direction here due to only caring about gravity, we only care about the Z direction for the force and for the displacement. Okay, so therefore, only use the components in the Z direction. Okay, so for example, Fz, now if we only use the force in the Z direction, that means we're working with 0, 0, 500, because the other components we are ignoring right now. And the displacement in the Z direction, same thing, 0, 0, 12. So to find the work done in the Z direction, it's going to be the force in the Z direction dotted with the displacement in the Z direction. So that's 0, 0, 500 dotted with 0, 0, 12. So you can see it's just going to be 0 times 0 plus 0 times 0 plus 500 times 12, which is 6,000 joules. So the work done by gravity, I mean, that's a pretty substantial amount of just the total work done, 7,600, but it's not the total work done. It's less than that. Okay. So hopefully we're doing okay so far. We only have one more topic to cover, and that is something called the triple scalar product. Okay. The triple scalar product, really, it's just this. It's one vector dotted with the cross product of 2 other vectors. So if I have vectors A, B, and C, this is what the A version of the triple scalar product might look like. So B cross C, I know that the cross product is going to return a vector. I can take that vector and then have it dotted with vector A. Now what's really important here is that you have to do B cross C first, and then you do A dot, the new vector. So let me just write that down here. You must do B cross C first. Okay? If you forget to do that, you're not going to make a mistake because there is no other way to do this. If you did A dot B, you would get a scalar. You cannot cross a scalar with a vector. You can multiply a scalar with a vector, but you cannot cross them. Cross product is only for vectors. So you have to do B cross C first, obtain the vector with the results from this, which is going to be perpendicular to both B and C, and then take the dot product of A with that new vector, which will in the end return a scalar, hence the triple scalar product. Okay? The product should be a scalar. Okay, so what does this even represent? Well, I want to remind you of something. Well, recall in the last lesson, what we saw was that if you take the cross product of 2 vectors, so let's say I have U and V, if I arrange them tail to tail, the cross product represents the area of a parallelogram. So in that area of the parallelogram is, well, the parallelogram you get by arranging the vectors tail to tail. So here we have cross product. So the magnitude of the cross product was the area of a parallelogram. Okay, now the triple scalar product also has a geometrical meaning behind it. Let's say I have my U and I have my V. Okay, so instead of A dot B cross C, maybe I have W dot U cross V. Okay, so I would have to do U cross V first. Okay, so U cross V, that's giving me essentially the parallelogram. If I dot that with a W, well, where's W? Maybe W's like this. If I dot that with W, what I'm actually getting is a three-dimensional figure. And it looks something like this. Okay, so essentially what I have here is a three-dimensional parallelogram. And this thing gets a very, very special name too. It's called a parallelepiped. That's a mouthful. Parallelepiped. Now this can go by different names. It can be called a parallelepiped. You replace the E with an O, or a parallelepipedion. So there's a few different words for it. We're going to call it a parallelepiped. So this is the triple scalar product. Okay, so if you take W, dot that with U cross V, this is the volume of a parallelepiped. All right, that's a lot of vowels. All right, so let's do an example where we determine the volume of a parallelepiped given the vectors that trace its edges. Okay, so example 4, and this is our last example, by the way. Vector U is vector 4, 3, 1. Vector V is 2, 5, 6. And vector W is 10, minus 3, minus 14. You don't have to draw out what these vectors look like. If you're interested, you can always use the applet that I shared with you for 7.4 and try to figure out, well, how these vectors look like in three-dimensional space, but really it comes down to this idea. You're going to trace out most likely, and I'll explain what I mean by most likely, you're going to trace out a three-dimensional parallelogram, parallelepiped. Okay, so what we need to do here is evaluate U cross V dot W. Okay, so U cross V dot W, that's the same thing as W dotted with U cross V. Okay, dot product is commutative. It doesn't matter which order you do it. Cross product, it does. Okay, so the first thing I need to do is figure out what the cross product between U and V is. So U cross V is going to be given by the following. So let's use our method from 7.5. So I have I, J, K, I, J, K. Vector U goes in the second row, so that's 4, 3, 1, 4, 3, 1. Vector V is next, 2, 5, 6, 2, 5, 6. Okay, so I'm going to use different colors here, but you get the idea. So I'm going to draw arrows going down first. Okay, so there's my X and Y and Z. There's the upward arrows. All right. So U cross V, I get a vector, so it's going to be 3 times 6, that's 18, minus 5 times 1. I'm not putting each number in brackets because everything here is positive. Right? If I have a negative, I'm going to be extra careful, but here it's going to be okay. J, 1 times 2, minus 6 times 4. Okay, and finally K, 4 times 5, that's 20, minus 2 times 3, that's 6. All right, 18 minus 5, that's 13. 2 minus 24, that's negative 22. 20 minus 6, that's 14. So there is U cross V. There it is right there. Now we take that vector and we dot it with W. So U cross V dotted with W. So we have 13 comma negative 22 comma 14 dotted with, and there's W right there. 10 minus 3 minus 14. All right, so let's take the dot product. So we have 13 times 10 plus negative 22 times negative 3 plus 14 times negative 14. Oh, not going to fit that there. There we go. Okay. And grab your calculator. 13 times 10 plus negative 22 times negative 3 plus 14 times negative 14. 0. Well, I'm sure that's not what you were expecting. How do we end up with a volume that is 0? Well, think about this. We determined this value by taking a dot product. That dot product, one of its components came from a cross product. When you take the cross product of two vectors, so u and v, I know that this result right here is perpendicular to both u and v. I know that automatically. Now I took that vector that is perpendicular to u and v and I dotted it with w. When the dot product of two vectors is 0, that means they are perpendicular to each other, right? So what that means is u cross v is perpendicular to w. It's orthogonal. So you cannot get, well, you cannot get a three-dimensional shape. So if you have u and v, imagine a vector that's perpendicular to these two. Imagine these two trace out this plane, right, shown by that parallelogram on the bottom here. They trace out a plane, u cross v. So u cross v is then going to be perpendicular to this plane. So it can be vertically up or vertically down. If w is perpendicular to that, well, you're going to get 0, right? So that would mean that w is most likely originally in the plane of u and v. Okay, we won't get into planes until chapter 8, but I just wanted to put that out there. What you need to just understand is that if it's 0, the volume is 0. That means that w was perpendicular to u cross v. So the dot product is 0, therefore u cross v is orthogonal to w, and the volume of the parallelepiped is 0, and that's because it doesn't exist. Okay, so that is it for this lesson. Okay, so thanks for watching 7.6, and we will end there for today.